This year marks 50th anniversary of the closed lectures, and this department is very proud of those lectures. We started in 1966, and there are some people in the audience who attended almost all of them. We had so far 23 speakers for closed lectures, and 13 of them are Nobel Prize winners, and the remaining 10 probably deserve Nobel Prize as well. Today's speaker definitely belongs to that category. We are delighted to have Professor Weiss from MIT. He was born in Berlin, but very soon ended up in New York City, where he grew up till he went to Boston to get a degree at MIT and then PhD. And at that time, he also worked with our own Henry Stroke. I saw Henry somewhere, well, right here. Henry's right here. And Henry still considers him as a youth. Since then, Professor Weiss, moved to work on big science projects, I'd say, and he's very well known for his contributions to the COBE satellite. That was a groundbreaking mission with the results that changed our understanding about the universe, and also as a byproduct generated 2 Nobel Prizes. And most importantly, of course, is his pioneering and persistent contribution to LIGO, the technology that he initiated, developed, and put through its completion. And another symbolic date is that in 2016, the collaboration announced the confirmation of direct detection of the gravitational waves, which were predicted 100 years before by Einstein, but also they detected merging black holes first time. So this is the subject of today's talk. Please help me welcome Professor Weiss.
Well, there's no seats back there. Can you hear me back, way in the back? Can you hear me? Raise your hand in the back if you can hear me. Wow, okay, I don't need a microphone. I'm going to tell you a story about Henry first. I don't know, I mean, you may have to give me 5 more minutes at the end, because I got to tell this story about Henry. And it's an interesting story relative to when he had just graduated, and you'll correct me if I say it wrong, please, okay? He got his PhD, he had gone to Princeton, and he somehow ran into Einstein. That's true, that's right, okay. And somewhere on Mercer Street in Princeton, and he told Einstein what he was working on, and he was working on nuclear physics, looking at the magnetic moments of strange nuclei, in fact radioactive nuclei, which was a brand new thing at the time. And Einstein didn't look very interested in that, at least from what he told me about it. And Henry then thought what else was going on in that lab that might interest him, and he said, they also work on atomic clocks. And that stopped him dead in his tracks. Is that right? Close to right. Close to right. Anyway, and so what Einstein wanted to know from Henry was, he explained how it worked. There's a cesium atom and has a very high frequency oscillation inside of it, and that oscillation somehow converts itself into going tick-tock, tick-tock. 10,000 megahertz, how do you convert that into tick-tock? And that was the principal question that Einstein was interested in. Imagine that, the technical question. Now, I don't know how he answered it, but later on we know the answer. It's electronics, but the fact is that Einstein was, of all the things that Henry told him, was most interested in that. The reason why I'm telling you that story is I'd be very interested to meet Einstein personally now and say, we've seen a black hole. And I suspect what he would ask me, because you'll see this in the lecture, he'll ask me, well, how did you do that? Not so much the black hole, but what did you do to make it possible to see that? And I'll show you why in a minute. So I suspect that would be the conversation. That's why I had to start with that story. That story was sort of right, isn't it? Sort of. He said it was sort of right. Anyway, so the thing is that when we celebrated Einstein's really quite remarkable discovery of the field equations last year, and 2015 was the 100th year after 1915. I got mine own. And it turns out that so what really is behind the Einstein theory, for many of you who don't know it, I'll just show a sort of first slide, which is much too primitive, but the way you want to think about it, and what this motivates is how we visualize gravitational waves, is that this is a diagram you often see. There's the sun, There's the Earth, and each of them make a little dimple in this membrane. What the hell is that membrane? And the way to think about that membrane is the following. Think that before the sun and the moon, sun and the Earth were put into that picture, there was a jungle gym, like what your kids play on. All these lines of constant coordinate in 3 dimensions laid out, and at each intersection in that place there was a clock. And the clocks were all synchronized together. That's the way you imagine what goes on. And then you plunk these heavy things into the picture, and what they do is they distort the jungle gym. And that is, in fact, the new theory of gravity. I'm giving you a very picturesque, but not very deep way of thinking about it. In other words, what one has done with this theory is you've replaced gravitational forces with distortions in the geometry of space and distortions of time. The clocks will run at different rates when they're near these masses, and space has become warped. It's no longer straight. All the jungle gym is no longer exactly straight. The lines aren't exactly straight. And now what the geometry does is it tells matter how to move. That's what it does. And so that's one way to think about it. And in that theory, then, you have gravitational waves. And here's what a gravitational wave looks like. Don't look at this for too long. I first want to say what it is, because you'll get dizzy. But the point is that what are gravitational waves in this thing? First of all, you had to have a news function. That was brand new. You couldn't use Newton anymore, because Newton, once you had special relativity, you had to have some way of getting information from one place to another gravitationally. And so consequently, the information can't travel faster than the velocity of light. So there had to be something that carried that information, gravitational information. Those are gravitational waves. And here are the properties of those waves that are given out in these 2 headings. They move at the speed of light because they have, the gravitons is a 1 over r squared law. Now we understand why that is. And the other thing is that they're generated, much like electromagnetic waves, by accelerating mass. Just as in electromagnetic theory, the sources of electromagnetic waves are accelerating masses. Here they are accelerating charges. Here they are accelerating masses. But because you only have one sign of mass, you're stuck with things which, if they are completely symmetric, they will not radiate. They have to have a quadrupole moment. They have to have an asymmetry. And that's the basis of it. So that's what these 2 statements are. They're transverse waves. And what you're looking at, now you better look at this. Here's where you're standing. And this is, imagine this is sort of a whole bunch of masses that have been spread out in space. They're out there let's stop their interaction between each other. They're not falling toward each other. Let's just turn that off for a moment. And here's where you're standing, and what is going on with these masses is a thing where you have space expanding in one dimension, and let's call it the x dimension, while it's contracting in the y. And as that wave passes by, it flips, and the y expands and the x contracts. So that's an oscillatory wave, which is a transverse wave. But what that picture really is a picture that at any one moment is a wave that has a constant strain in it at any one moment. And that strain then varies. And what's the strain? That's the field quantity, like the electric field in an electromagnetic wave. In other words, what the strain is, it's a change of distance between 2 of those masses divided by their separation. It's a ratio. And for example, if you look at these 2 masses that are closest to where you're standing, those 2, for example, they don't move very much, but they're also quite close together. Now you look at these masses over here, that guy, and they're moving a lot, but they're also further apart. So the thing that's constant in that wave is delta L divided by L. And that's very important that you get that, because the whole basis of detection is related to that. Okay? So they are waves of constant strain. Now, interesting thing, in 1916, Einstein didn't in 1915 write a paper that had gravitational waves in it. In 1916, he wrote a perturbation paper, a paper that was an application of the field equations, but in the very weak fields. And in that, he showed again that the Newtonian limit was a limit that his theory had. He showed, once again, there was bending of light. He showed the perihelion advance. We'll get that again in a minute. But he also talked about gravitational waves for the very first time. And in that paper, he gives us the properties of it that I told you about. And he says something really quite remarkable at the end of the paper. He makes a mistake in the paper. That's not important. It's important, yes, but it's not important for what I'm about to tell you. Because the thing that I'm going to show you is that he writes a result at the end of the paper which says you'll never get to see these things. And here's the way, he says in German, but you can read the German, there's a Siegmann, I'll read it in English. In any case, one can think of A which is a quantity which is the amount of power carried away by a varying moment of inertia with time. This is, in fact, these constants that are in there. And there's a c to the cube, and there's a g, and a whole bunch of numbers, and he says so. That in any case one can think of, A, this is the quantity, the power carried will have a practically vanishing value. In other words, he says outright, this is never going to play a role in physics. And you have to now, and I've asked people who look at the Einstein papers to do what I've done here and making believe I was Einstein, which is sort of presumptive of me. But the thing is, what I said, what must have he gone through to make that statement? And so he might have, here is a formula that is one that he might have used. So you can be part of this too. Let me at least tell you about this formula. That's H. Well, H is, in fact, the strain that you saw in that picture of the dots. That's delta L over L. And you can write it in two ways. You can write it as that if you have a system, it's made, there's the Newtonian constant G. M is the mass that's involved in the motion. R is the distance you're away from it. And C squared is the thing to normalize this quantity so it's dimensionless. In fact, that quantity is the dimensionless measure of the strength of the gravitational field. On the Earth, for example, that's 10 to the minus 10. At a black hole, that's of order 1. Okay? And then, here's the thing that puts in the dynamics. The velocity squared of the system divided by the velocity of light. So if you can put some numbers in this, and I'm doing this in these little examples down here, you can get an idea of the value of H that Einstein must have calculated. And I'm dying to see the back of the envelope or the notebook where he did this. But nobody can find it. I've talked to a lot of historians of science. And so let's do it ourselves. So you now say, okay, suppose he imagined two trains. I mean, trains are possible. He could have thought two trains colliding with each other. And he made that number. Let's do the number ourselves. Say 10 to the 5 kilograms for a train. The velocity is about 100 kilometers per hour. In 1960, that's quite possible. And the collision lasted maybe a third of a second. I mean, and you have to be far enough away so you're in the radiation zone, not in the induction zone. So you have to be at least a wavelength away. So it's 300 kilometers away, and that's the R you would use. And you get a number which really is infinitesimal. H is about 10 to the minus 42. And that is unmeasurable. I mean, even today. So that's probably the first thing he did. Well, then he said maybe he would use a telescope and look at a binary system, which is a good system of stars that are going around each other. They're perfect examples of a system that's being accelerated in a non-spherical way to a binary star system. Well, what might he be known about? Well, the binary star systems he might have known about had a solar mass. There might have been a period of a day. You see a lot of those systems like that, white dwarf systems. And it might have been, and at the time the galaxy was not yet known, but probably somewhere around 10 kilo light years away. If you got enough, he might, or maybe 3, it doesn't matter, it's only linear in that. And so he would have gotten an H for that of about 10 to the minus 23, which is reasonable. That's something which one maybe nowadays could detect with a half-day period. But he wasn't thinking of detecting them because he couldn't know how to do that. Because he hasn't asked us the question, how did we do it, okay? But on the other hand, he probably would say, could you have seen this change aspect? Could you have seen the thing change its shape due to the fact that it was radiating away energy? And that's the number. And how long would this have taken for this to change perceptibly, let's say by a fraction, a tenth of a solar diameter, one of those? They got closer together. It would have taken 10 to the 13 years for that system to do that. At that time, people didn't know the age of the universe, but we know that's much longer than the age of the universe. So he's quite justified in saying this is not anything that's ever going to play a role. And so what happened? Well, what happened is 100 years of two things. And one of them is this thing. One of them was actually a stunning discovery, and I'm talking about it experimentally. Let me say a little before that experiment was done, or observation was done, the history of gravitational waves and all the idea that they might be real or not real had gone through many, many oscillations. Not that Einstein varied, he himself sort of doubted it in 1936. There's a long story about that. You ask me in the questions if you want to hear more about it. But he himself never really came around to the idea that this would play a role in science at all. And so these two guys, this is Russell Hultz, who was a graduate student at the time. This is Joe Taylor, who is, when they did this, Joe Taylor is now a professor at Princeton. He's in the plasma physics nowadays. But these both were at the University of Massachusetts in Amherst. And they came across, as being radio astronomers, they came across a system that was really quite remarkable. This is all in your time, in my time. And what they discovered is they discovered the pulses that came from it turned out to be a neutron star that is a pulsar. and it was going at about 17 hertz. That's what they heard that in their radio telescope. They heard that. That's all they ever heard. There's nothing more than that. And so consequently, after they watched this for a while, listened to it for a while, and found out it sometimes got a little faster, sometimes a little slower. And that going faster and slower had a period of its own of about 8 hours. And from that, they figured out that there was another star that they couldn't see. They couldn't see either of these guys. There was another star, and they guessed right. They guessed that this was a pulsar. I mean, a neutron star. And then they did the calculations using only the pulses. They calculated what must be the orbit of that thing, knowing just only from the dynamics of those pulses. They got the dynamics of the stars, and they got a lot of the things that were seen in general relativity very quickly. For example, they saw the aphelion advance. Within about, there was 4 degrees, not 43 seconds of arc in a century. It was 4 degrees in a year, because these were real close. They have enormous, the value of G is, at the value of G, value of the gravitational, that gravitational dimensionless parameter is about the same at the sun from here. So 10 minus 6, it's a huge field. The field of this one at that one. So you're talking about the field of the sun. You're dealing with 10 to minus 6 for GM over RC squared. It's a big field. Nothing like a black hole, but it's bigger than anything we have on the Earth. So this thing, what they saw, and this is the thing that clinched it. What they saw is that these guys, as time went on, and they saw it from, they started in 1973, and I think they were still doing it. People are still doing this now, but they quit at about 2000. They won the Nobel Prize for this in 2003. So, and what they saw is that indeed that period was getting faster. They were getting closer and closer, and that's what this curve is. This is the change in the period. It's in seconds, I think, and it gets shorter and shorter as a function of epoch. And these are the dots these are the dots that were their data. And this is not a fit, it's the straightforward calculation where you solve for the masses using relativistic dynamics, all in general relativity together. You get this curve without trying to do a fit. And that is indeed, that curve comes from the energy loss due to gravitational waves. So these were the guys who, by inference, first saw gravitational waves. It settled all the nonsense that was going on theoretically about factors of 2, whether Einstein had the right. One of the big problems was his idea, the formulation for the energy in the gravitational wave vis-a-vis the strain was a pseudo-tensor. It changed sign on reflection. People didn't like it. There was all sorts of problems, theoretical problems with the formulation. And finally, this settled it. It settled it that Einstein's formula for the quadrupolar radiation was right. That's it. There was no more discussion. And it also told us what we could look for if you built a real gravitational wave detector. Okay. So the first guy to try to do this was actually Joe Webb. And this comes from the Chapel Hill Conference in 1957. Now, Joe had worked with, he'd been a radio astronomer, he'd been a microwave spectroscopist, then a radio astronomer. And he invented some ideas about masers, but he got captivated by the idea that you might be able to do an experiment to measure these very small strains. And his idea, much supported by John Wheeler, was to take a great big bar. This bar, for example, is now in the Smithsonian, and instrument it with strain sensors. And the idea was that a gravitational wave would come along, go through the bar, cause it to stretch, and then after the wave had gone through, the thing would ring on, and you would be able to listen to the thing ringing. That was the idea. As though the gravitational wave had bopped it with a hammer. Okay? And to his misfortune, he saw things. Okay? He saw something. And what happened is that a whole bunch of people in the world later on did not find that. They could not, he published in 1969, he published a paper which was really quite dramatic. I have seen gravitational waves, and he saw them from, he didn't know what, from the galaxy. He thought he'd seen an extra amount of gravitational waves when the detectors were facing in such a way they would see best the galactic center. And the way he did it ultimately was to make 3 of these bars, put one in, was one near his office in the University of Maryland, another one in a golf course near the University of Maryland, 8 miles away, and they saw coincidences in those 2 first. Sort of a coincidence, maybe 1 an hour, which is really fast, too many. Then he put another one at Argonne Laboratory in Chicago, in a stairwell there, and he saw 1 or 2 per day. And that's when he wrote the paper. He thought that he had seen this, and then a whole bunch of people in the world These are all the groups that went and did this. I mean, all over the world, this was a dramatic result, did what Weber did, and they couldn't see anything. And the guy who was most influential in actually killing this all off was Dick Darwin, who was in New York at the time. He was a head scientist at IBM. And he did it completely differently than Weber. He did it smart. He built a little bar, but understood exactly everything about it. And he saw nothing in one bar. He didn't even do a coincidence experiment. And he could prove to himself that there was nothing there at the level that Weber was talking about. And there were really quite acrimonious debates at physics society meetings. Weber and Darwin standing in front of everybody, one accusing the other. Very much like the debate between Trump and Clinton. Okay? It's really quite similar. And so, and this in fact gave a very bad pall to the whole field. In fact, it was sort of difficult to start LIGO in that milieu because it was considered, in fact, it was considered sort of crazy science. Okay. All right. So these are people who carried on. There are people still doing it. Now, the spherical bars are still being done in Brazil and in the Netherlands with cold bars and trying to make them better. My own guess is that they will see something eventually, but they're nowhere near as flexible as the idea of using an interferometer. It's not that I want to say this is a better idea. There is, what's fundamentally behind it is that if you want to get a big system, and you know, that's why I told you about the strain, you do better using something that's coupled with light, because you can make it much larger, by 10 to the 5 times larger than something which is coupled by sound. And that's the fundamental difference between interferometric detection and acoustic detection. Okay? So you'll win if you want to start a field with acoustic. Now let me explain the acoustic detection to you. I mean the interferometric detection to you. And what it is this is a little cartoon that was written for kindergarten kids, but we're all kindergarten kids at this stage. And what it is this is a laser, and that's a beam splitter, and you're sending light from this to the beam splitter. There is a mass, like one of those dots I showed you, and the light will go there. You're going to try to measure the motion of this mass versus the motion of that mass. There's light going to go to that, and here's a detector. So let me get this thing running, and that is a Michelson interferometer, nothing more than that. And you'll see what's going on. The electric field is what's being shown. The red indicates that there's power, there's light power. It's a helium neon laser. It hits this mirror, comes back to the beam splitter, and same thing is going on in this arm, and if you make those two exactly the same length, you will get no light to the detector because the electric fields cancel each other. Now, you start wiggling this mass, let's say, in and that one out, and you'll notice that you will get light at the photodetector. That's as simple, and the whole image goes dark and light. It's not lines like the Michelson experiment. And that is the basis of the detection. There's no more than that. That is, I mean, if you really have to go down to the bare essentials, how do you detect gravitational waves this way? There's no light, you set the trap, make the paths equal. The gravitational wave comes down on the system and lengthens one arm, shortens the other, and what happens, light doesn't take the same time in the two arms anymore, and light shows up at the photodetector. It's simply that. It gets gussied up to get the sensitivity. We'll talk about that in a minute. And here is another way of thinking about this. And this is only for, we had a little talk this morning to the professionals, the experts here. This one I think is good enough so that you ought to know it too, because it helps in understanding what follows. A way of describing what I just talked to you about is the following. Here's the same thing you were just looking at. Here's that laser. Here's that mass, the test mass, and there's another test mass over here is the beam splitter. And there's the photodetector. Now what happens here is sort of very interesting. What happens is the light, these arrows, this blue arrow or the purple arrow always indicates the direction of propagation. And what you see here is that there is this red arrow is the carrier, the light that comes out of the laser. So it's heading to the beam splitter, and then it heads to the mirror over here, and then it's still just it's about 0.7 of the value it has here. And now it comes back from that mirror, and now it has some sidebands on it. Phase modulated sidebands. These are due to the fact that that mirror is vibrating back and forth at the frequency of the gravitational wave. And this is an upper sideband that's at the distance. This is the laser frequency. That's the laser frequency plus the frequency of the gravitational wave. That's the laser frequency minus the frequency of the gravitational wave. They're phase modulated sidebands due to the fact that this is wiggling. And the same thing is happening on this arm. Here you can see the light going out to it, but now they have, because of the opposite sense, this one is coming in first and then going out. This one's going out first and then in. The phase of these two sidebands are opposite. This is positive, this is negative, this is negative, that's positive. And they come to the beam splitter, and the beam splitter is a device that has a reflection. On reflection causes the electric field either to not flip, which is the plus sign, or the anti-symmetric side causes the electric field to flip. And so what happens is none of the laser light, the carrier, gets to the photodetector. That's why it's dark. That's what you saw in that other picture. But the sidebands get amplified because they get both flipped and they become in the same sense. So these sidebands get much larger. And that then is what's detected the photodetector. And so what happens now is as you get more and more light, the sidebands get bigger and bigger. And you can see exactly how this detector works as a function of a lot of different things you're now going to see as wrinkles in this idea to make it work so that you can measure the following. You have to improve over the simple thing of just thinking about the wavelength of light. You have to, because we're now, and I'll get to this, you have to get to strains of 10 to the minus 21. And that's the thing that all the theorists, not at the time of Weber, began to say to us, look, if you're going to try to measure something, there's no astrophysical sources that makes strains much larger at the Earth than 10 to the minus 21 strain. And now in 4 kilometers, which is what this detector is, you get a motion of about 10 to the minus 18 meters. And that's where people begin to throw you out the door, because this is just too small a thing. And let me at least help you understand that a little bit. And don't be denigrated. It's useful to go through this for some people. What is then? Here's a meter. And of course, in America, people know what a meter is. It's 3 feet, right? Okay. So you have to go. This is all the little steps you go through. So you divide by 10,000, you get down to the size of a hair. That's still understandable. You divide another 100, you get down to the wavelength of light. Now, what you see best is about half a micron. That's green. That's what this laser is. But we use green. We use infrared light. And so you're not there yet, but you can still have an idea in your head about this. And you can just about get to another factor of 10,000. You get down to an atomic diameter. And you can prove that to yourself very nicely. And we do that with kids all the time. We give them a medicine dropper. And we say, here, look at the medicine dropper. Drop a little oil into a puddle of water. Drop it. Measure the volume of the little drop. And then look at the area of the colored fringes that you see in the puddle of water. And then from that, since the volume has to be the same, you can get the height. And that height is a few atoms high. So that's still within your experience. But then it gets too far. So then you have to go another 100,000 to get down, and you get down to the size of a nucleus. And finally, you get to where we need to be. With another factor of 1,000, you get down to 10 minus 18 meters. So that's the point where there are 2 challenges then in this whole business. One challenge is to sense a motion that small. That's challenge number 1. So you have to go from a wavelength, which is 10 to the minus 6 meters, to 10 to the minus 18 meters, which is a factor of 10 to the 12. But you also have to make sure the thing you're looking at, that mirror that you're looking at, doesn't wiggle more than 10 to the minus 18 meters due to other causes in gravitational waves. And that's a much harder proposition. And it turns out why. It turns out another factor of 10 to the 12. Why? Because you're sitting here in this room and it's wiggling by a micron. It's wiggling by 10 to the minus 6, a few times 10 to the minus 6.
Wait for the subway.
Not just the subway, no. It's much worse because of the subway. When the subway goes, it probably goes up by a factor of 30.
You'll hear it.
I'll hear it, but you'll feel it maybe. Then it's too much. But no, the typical, in a quiet place, like out on Long Island maybe, without the Long Island Railroad running, okay, you will have a few microns, okay? So you got another factor of 10 to the 12 to get rid of. And that's the hard factor to get rid of. So let's talk about that. Okay, so here's the first bit. These are people who are in different places. The guy who actually was very important in this whole thing is a person who doesn't get any of the heroics of Einstein or Wheeler or anybody. It's a guy named F.A.E. I'm just curious, how many of you know of him? 1 or 2 people, I see. Okay, well, he's the hero. And he, at that Chapel Hill conference, finally settled the whole argument of that you could make measurements that were invariant about the strength of gravitational waves. He was the first guy to really show people how you could do that. Make measurements at one point. He, in fact, invented the idea of using light, but he didn't say it quite right. He certainly didn't know how to do it. But the idea of measuring space with things that were invariant measurements, scalar measurements, is something he invented. And he is actually he's the originator of a lot of important ideas in making relativity measurable. So he was used in this thing, which was designed at MIT first, and I won't go through this all. There are ideas in here which were really developed by others, which I'll get to in a minute, Here's the first group of people who worked on it. These were all graduate students. They couldn't work on it very long because, well, it didn't make any science. And at MIT, I'm sure it was true at NYU as well. In the 70s, if you wanted a PhD, you had to do a piece of science that was publishable. I bet you that was the case here. Mm-hmm. And you couldn't publish the fact that you might have worked on an apparatus that got the best distance measurements because you didn't measure a new thing in physics. You could not get a physics degree out of the technology of making a thing like that. So I had to start graduate students on this and then put them on something else so they could get a degree. Okay? And that was, this is sort of a gang who built the first one, and they built a thing which effectively had two ideas in it. It's the same idea as what you saw, but it bounced the light back and forth many times. That gets you a factor of the number of bounces. And then it also hung, these were all hung. Everything was hung. Imagine doing interferometry hanging everything. Everything is jiggling, you have to servo it, make it not move. There were two fundamental ideas, and then the other idea was you do something to modulate the light so you get out of the 1 over the F noise. Let's not get too deep into that unless you ask me questions. Now, the people who really made this idea work were the first group, was the German group. This is a group at the Max Planck Society. At that time they were in Munich. Now they're in Hanover. And this guy is Billings, and look at, he's got a Weber bar. That was the same situation with Ron Drever, who was in Scotland, and they both had been working on Weber bars, and they were trying to figure out what the hell to do next. Either get out of the field, which was a lot of them did that, and some people stuck with it. And they decided that once they saw what was being done at MIT, they decided that was a good idea. And these guys, all of them are, this guy's still alive, he's 105, and he's alive, he's in his 80s. And everybody else, unfortunately, has died. And many of the ideas that have come up, how you do this, how you float the masses, how you stabilize the laser, how you can make the light more powerful by recycling it, all sorts of things you'll see in a minute, came from that group. The other group, a little later, that didn't do as well as was the group around Ron Drever in Scotland. And these are the people. They're still all alive, and they're very, well, no, he's not alive. He died in a mountaineering accident. But he invented the idea of, well, we'll get to it, it's what's called signal recycling. We'll see what that is in a minute. And these two are, they're still doing, in fact, these two people were deeply involved in LISA, which we'll get to at the end of the talk. So Ron Drever left Scotland and took a job at Caltech and became part of getting the LIGO project running. Okay, so this was the group of people who did this kind of work in the 70s. And what is built now is this instrument. And this is the actual instrument that made the detection, just a schematic of it. And you'll see everything is the same in it. Well, not everything, it looks a little different, but here's the laser, there's the beam splitter, there's that far mirror. And there's that far mirror. Now there are these extra mirrors in this system. This mirror and that mirror, this makes the FabryPerot interferometer. These are cavities, and so what they do is they bounce the light back and forth about 300 times. That increases the sensitivity by about 300 to the motion of that mirror. And that's done the same way, exactly the same way in both arms. And that idea, the idea of using FabryPerots came from Ron Drever. We thought of him at MIT. I thought it was too complicated. And it took a long time before we used delay lines. And it took a long time before that was actually made practical. But it was a good idea. The other ideas that are in this, so the bouncing around the light 100 to 300 times. The other idea was this mirror, which is a very clever idea. This was had by both Drever and the German group together. And in what order? I think the Germans had it first, and then Ron had it later. But the idea was, since there's no light going to the photodetector, and where's all the light going in? It's all coming back to the laser. It has to go someplace. What you do is you make it so that you put a mirror here with a given position and a specific transmission, so that no light, you have two beams. A laser beam that would hit this and reflect, and then the light that comes out of the interferometer that would be transmitted by this and go back to the laser. You can make those two beams cancel each other. And what that's called matching the interferometer to the laser. And so what you've done now is you've taken all the light of the laser and put it inside the interferometer. And so, for example, on LIGO that we now operate, you have maybe 500 watts of light. This is a 25-watt laser that we're now trying to make more powerful. This is 500 watts in this thing, and it's about half a megawatt in here. Okay, it's huge amounts of power. All that power is now heating up the mirrors. That's what it's used for. It doesn't go back to the laser. The other idea is much more subtle. And this was an idea that Brian Mears and Ron Drever had. Brian Mears, the fellow who died in the accident. This is a very clever idea and much harder to explain. But I'll tell you, since you know about sidebands, And I'm not going to show you the picture, but I'll tell you what it does. It manages to reflect the sidebands, that is the gravitational wave sidebands, back into the interferometer so they can be used to be further being excited in this cavity and that cavity. And by doing that, if you put this mirror in the right place, and you can move it all over the place, and make its transmission right, you can affect the spectral response of the interferometer. You can change it completely. You can change it from a broadband system to a very narrow band system. It's a very elegant idea. And LIGO, for the first time, is using this. I mean, the initial LIGO, we didn't have that. So that's part of what we call advanced LIGO. Okay. So here is now a little more of the history. This was the proposal. Turns out Drever, Kip Thorne, and I tried to run this project. We failed. We couldn't agree on things and so what happened, the committee said, look, you get yourself a director. This was the first director. And he was a very strong individual. He helped us write a marvelous proposal. And he did something very clever. He coupled, and this is when you think of big projects, this was really, really clever. What it was is he took the people who were the scientists who knew about the interferometry and coupled each one of an engineer who was responsible for a particular subsystem of the big construction that was now going to go on, and coupled them together. For example, I was coupled with a guy who worried about the long beam tubes. Mike Zucker was coupled with a guy who was worried about the vacuum system in the individual buildings. He was a scientist. He was coupled with a civil engineer who worried about the buildings and so forth. And why was this done? Because there were all sorts of requirements that were on the standard things which could have been missed if there were people there who understood what the requirements were for the instruments. So that was a very important thing to do. And okay, and what this then is the very first LIGO detector, and this is the noise in it. And I don't want to dwell forever on it, but what this is a picture of is H, but now it's as a spectral density. So this is H per unit bandwidth. Okay, this is a spectral density of H. And this is now frequencies. That's 10 hertz, 100 hertz, 10 kilohertz. And if you want to get an RMS value, for example, let's say at this point, you take, and here's 10 to the minus 23 H of F. Now you take the square root of that, multiply that by 10, and you wind up with the RMS sensitivity in this region right here being about 10 to the minus 22. So it's 10 times better than what was needed and that's in fact the first runs we made. And here are the things that limit it. We're limited at the high frequencies by the shot noise, or in other words, the quantum noise of being able to read the phase very carefully of the light. We're limited in this region right here, just that region, by the fact that the mirrors are at room temperature and they get kicked around by thermal vibrations. Okay? And then we're limited here by just the fact that we weren't clever enough to get rid of all the ground noise. That's all the seismic motions of the Earth that's still with us. We had to do much better on several of these to be able to make the detection. We'll get to that in a second. The other noises that are in here, there are two that I think are worth pointing out. One is, and I pointed this out this morning, this is this line right there, which we're at, which is the thing that made the thing so expensive. In other words, you had to make a vacuum for that 4-kilometer tubes so that you didn't make index fluctuations due to the fact that the number of atoms in the column were always the same. There are always atoms going in and out of the optical column. And that makes phase fluctuations in the light. And in order to get that to be smaller than any, you have to use, we were operating at very good pressure, 10 to the minus 9 torr. This is a noise which is the reason why it's important to go into space. And we're not solving this by any better techniques than what's in this picture. There are no techniques. And what it is really this. You can get rid of the seismic noise by using the fact that you're measuring motions against the inertial frame. You have a reference. The reference is where F equals ma really means something when you use this. A is with respect to the inertial frame, and you can always measure your A with respect to the inertial frame. That's possible. Use seismometers, you can use instruments to do that. The thing you can't do is those things on the Earth that cause density fluctuations in the ground or density fluctuations in the atmosphere. They pull on our mirrors. In other words, here's a density fluctuation because of a ground wave. It's a P wave. It causes a longitudinal wave. It compresses the ground here. And here's a mirror. And that mirror gets attracted to the ground more when that is condensed than when it's rare. The same thing happens in the atmosphere. And that's what this curve is. This is something that is just Newtonian forces. And you can't shield that. And we're trying to figure out, maybe you could measure it a little better than we did, but that is something you can't get around. And look at the steepness of this curve. It's enormously steep. So that is a fundamental noise on the ground that we won't be able to beat. And now here is the same situation now for the advanced detector, the one we have. And what's done is, this is the same curve, as you were seeing before. It looks very different. So again, frequency versus h of f. And let me show you what's in that detector. First of all, that made it so that what's limiting us now, I might as well tell you, that line right there is the limiting line. You can see the quantum noise, which is the measurement noise, is this purple line right there. And I didn't mention that in the other picture, but this is due to radiation pressure fluctuations on the mass, and this is due to the phase fluctuations of the light. And so consequently, it turns out you have built a Heisenberg microscope using that mirror as the basis. If you put more light on it, yes, you will improve your phase sensitivity. That's the same as position sensitivity, but you will ruin your momentum noise. It gets worse, and that's what's going on. So that there is a quantum limit to this. But this line is the one that will limit us. We're not there yet, and that is simply thermal noise in the coating itself. That very elegant coating that has 40 layers, that's each one a quarter of a wavelength thick, is on that mirror. And that internally has a lot of losses, and it is the thing that dominates the motion of the mirror thermally now. Very high. So now what we have is we have four pendulum series. This one, that one, that one. They all hang from each other. Each one gives us a reduction in ground noise and thermal noise from the stages above by 1 over the square of the frequency per stage. Now, the other thing so this is hanging from this thing up here, which I only described to you. But that's something that's useful maybe to you guys. What it is using the idea I just told you. Namely, you use seismometers. This is hanging from one stage and another stage, and the inner stage has a seismometer that measures the motion of that platform. There are forces that are on the outside of this thing which push the platform so you null the seismometer. In other words, you're getting rid of the ground noise by putting forces on the platform, so you get rid of it by putting forces on that are just equal to the forces that come from the ground noise. And that's a very, very important technique to do low frequency isolation. It's done twice in that system. And that is what this entire thing hangs from. And that is actually what was needed to make the discovery. I'll show you where you'll see that in a minute. So that's something you guys might want if you have experiments. They cost a lot, but if you really are stuck with living in a place where there's a lot of motion at low frequencies, 1 hertz and lower, or maybe 10 hertz and lower, you could build this or have somebody build it, or you could get the LIGO and ask them to give you the designs. It could be used for a lot of different tricks. So now let's get on to this is the last, then I'll show you the discovery. But this is I just want to show you this curve because it shows you really how the progress went. This is now the same curves but with real data. This is frequency, this is now h of f again, and the very top curve is this red thing, which is the curve that Virgo has, which is a system that is in Italy, very comparable to LIGO, and that was the sensitivity they had when they were running with us in the initial detector. And then at that same time, LIGO had a sensitivity of this purple thing. It's better at these frequencies, then it gets much worse at low frequencies. And that's it. And that's as far as we got with the initial detector. We saw nothing. We saw a pretty clean nothing. Here is the curve that is it's the same curve that made the discovery. It's that's this curve right there with the advanced detector. And you can see the big change between here. In this region is where much of the energy of the black hole is. And look where we were. That was running off scale. So we had hundreds. By the time you got hundreds in the region of improved sensitivity in the region where the black holes were important. We didn't improve things dramatically yet where the neutron stars will be. And this is the curve that we should be at. Let me just see you there. It's this blue curve right there. That's what you would calculate where we ought to be right now. That light blue curve. And we notice there's a discrepancy. And I think, as I told people this morning, I think we found some of that yesterday, as a matter of fact. Here's where we ought to be when we finish advanced LIGO, right there. This will be where that is that curve, which had that noise curve. It's another factor of, well, maybe 3 in most places. And then here's Virgo. When it gets its new instruments on it, which they're busy trying to do, it'll have a curve that looks like that. It's 3 kilometers long. It's not going to be quite as sensitive. I won't go into these. These are things for the future. Now, there are ideas of how to make this something a lot better still. Okay. So now let's get to the to the actual discovery. What time? How much time do I have? Tell me.
We started late, so you have 17 minutes.
Oh, so okay, let's make it 20. Do you mind? Okay, I think that'll do it. 20 minutes says you'll have to suffer another. Okay. This is where the detectors are. These are the two. There's one in Washington State. There's another one in Louisiana. And those are the two in the United States, and they're operating. Here's Virgo, which is near Pisa, which is right about there. They were not operating at the time. They have operated, but we're not operating at the time when we made the discovery, which is unfortunate, as you'll see in a minute. And then there's another research detector, which is actually, those of you who are interested in shorter interferometers, there's one that the German group is running in Hannover. That's called GEO. And those are the existing detectors. There are plans to put more detectors in Japan. That'll be ready in about 2019, they hope. That's going to be in the Kamioka mine. And then there is a LIGO detector that comes from the LIGO instruments being built in India. And the idea of all of that will be to better define the position on the sky where the sources are. I'll get to that in a minute.
What about earthquakes in Japan? Earthquakes.
The earthquakes are the only problem. We have earthquakes that are terrible in the Pacific Northwest. Earthquakes are a problem if they are continuous and if they destroy the apparatus. But we, that you don't want to build in an active zone. But the fact that we're dealing with earthquakes, it doesn't matter if they go around the Earth all the time. They're everywhere. Yeah. So you're stuck with them. And that costs your duty cycle. That's fundamentally what it does. Okay. So I want a quick movie of, this is my quick thing so you can look at, this is LIGO in Louisiana. And this is LIGO in Hanford. This is the beam tube in its enclosure. That's the end station. That's a mountain. This is in Louisiana, again, all trees. And then this is the beam tube itself without its insulation. And here's people working on a laser table. For example, this is a laser table that is used for the output detection. Here's the control room. And these are people who are learning how to control the interferometer, being taught by one of our scientists. So that's that. You've got a little tour of LIGO. Okay? Very short tour of LIGO. Okay, now let's talk about the detection. Okay. Now, remember, we had this, the surround that we had was the Weber. We still had to deal with Weber. People are still worried that you will somehow find something that's not there. That's most fundamental. So we built this instrument to the best knowledge that we could. And what we did is we made certain demands. First demand is that you build two of these instruments, and they see the same waveform at both places to as best as you can do with the noise, and that they are within 10 milliseconds of each other. Okay? You don't know where the source is, so you have to allow for that. We believe the gravitational waves travel at the velocity of light. Okay, the other thing is we have sensors for all the stuff that's going on in the environment. You make sure you have magnetometers, you have seismometers, you have sound meters, you have RFI instruments. You have line voltage, all sorts of wind speeds, everything you can think of. We even have a muon detector because we're worried about the showers. This is not. And if any of those instruments show something coincident with the two signals that you see in the two detectors that are the gravitational wave detector, you say, no, we cannot accept that signal. That's almost done automatically. On top of that, and this is the thing that really is expensive and troublesome, there are about 100,000 other signals that come out of the instrument, and they're all monitored. I'll give you the laser frequency stabilization, the amplitude stabilization, the pointing of the mirrors. I mean, I'll just give you examples, or many, many other signals. And you measure all of those, they're internal signals to the interferometer. And again, if any of those show a noise that is commensurate with what you think could cause trouble, you reject the signal. And that's where this whole process is what takes 1,000 people in the end to do the data analysis. Everybody has to incorporate these vetoes into whatever different classes of sources they're looking for. Okay, so here then is what you saw in the paper. Let me quickly describe this to you. This is the big result. And this is then what was seen in Hanford. This is now time, very short time, 0.25 to 0.45 seconds. And the amplitude here runs from, that peak amplitude is about 10 to the minus 21. So the guess of 10 to the minus 21 wasn't so bad. Okay? And this is the signal. This is probably noise in here, but eventually you see a signal that's developing. And there it is. That's probably noise, as you'll see in a minute. Here is the signal. The blue one is the signal you see in Livingston. That's the Louisiana site. And they are superposed on top of each other. They're not exactly the same, but they're close enough to being the same within the noise. And here is then, below this, is a theoretical waveform, which you get first by looking at gross things in this thing. There are analytic solutions you can get without having to go through the whole numerical process of solving the Einstein field equations, which are very important. But you can do a lot of things analytically first. And you get then the order of magnitude. And you can see that you can't see it very well, but there's a gray area behind this, where up to about there, which is all analytic, with given parameters, which is 30 solar masses in both round numbers. And then there's a part that you have to use numerical solutions for, which follow this to in the region where they collide and really ultimately make a black hole, as we'll talk about in a minute. And now here's the residual between that theory and that data, both for Hanford and for Livingston. And it looks pretty white. Those are the residuals. And now there's a thing that's very important that you understand. When you compare this against the theory you're going to see in the next picture. All of these things have been filtered by a thing that looks like this. This is frequency versus the transmission function of the filter. And what is that? You can't read it, but I can tell you what it is. It's a thing that is the same as you have on your audio or your radio. If you have a lot of rumble, you turn down the bass. That's turning down the bass. If you have a lot of high frequency hiss, that's turning down the high frequencies. Okay, that's what it is. That's all what was needed to see this signal with the video as exact as it was shown. You didn't have to have all the fancy techniques that you'll hear about in a minute to find this signal. It's an enormous signal. And now the thing is that the next picture shows you the actual, what we divined out of that. Whoops. And what it is you can see this gray thing that's behind. These are the analytic solutions. The red ones are the numerical solutions. And down here is the velocity of motion of the. In green, you can see the velocity starts at about 0.3, the velocity of light of these objects, and they're getting close to 0.6 the velocity of light. Okay? And so at about 0.3 the velocity of light, or maybe a little better than that, maybe 0.4, this thing begins to be unreliable, and you only can get this thing with the straight numerical solutions. Now let me tell you what is going on. This is what this picture is. It shows you the two black holes when they're sort of in their Newtonian region. They're not changing frequency very much, but here the gravitational radiation is getting quite demanding. And you can see the frequency getting higher and higher. And eventually the two holes collide, and then they make a new black hole. And what happens in this region, which we did not see with any precision, we did not see that, is the ring down of the geometry. When the black hole forms, you'll see this in a picture, in this thing I'll show in a second. We did not see that well. But that's been predicted for years, and we will as we improve this system. Here's a movie that was made by Kip Thorne and, people in Caltech and the people in Cornell together of this whole thing. And what you'll see is the waveform is, when you get into the regime where we are, it's down on this bottom here. Yeah, you're getting in now. Here are the two black holes. And what the colors are, wherever there's a huge dilation in the time, is red, and it gets blacker. When it's black, the time stops. These little vectors are effectively the gradients, the things that tear you apart as you get closer to the black hole. So, and now what's happened is the time, you can see this is all very slowed down. These black holes are getting closer and closer. There are gravitational waves being emitted, and we'll see in a minute what happens. And now I think they stopped the movie for a second here as things about to form the new black hole. They're now getting closer. Well, there, and you can see that time has sort of stopped inside this thing. And then here it is, the point where the two are just about to form. And now they froze the movie, and there's the new black hole. And this thing, which is now the fact that the space continues to relax after that, we did not see. These are the normal modes of the geometry, which we did not see. But we will. I'm sure that they're there. So that's the thing. And now let me show you something about the data analysis, so you'll understand that.
So how long was that whole movie that you just showed us?
It's about 0.4 seconds at most.
Wow.
That's it. If that, be more like 0.3 seconds.
How fast are they moving?
Well, they're moving at the end. They're moving at about 0.6 the velocity of light when they hit each other. Imagine. And here's we'll get to that. Let me first show you. We'll get to the summary of this in a second. So let me show you how the data was analyzed, which is very important that you understand this. But there are two methods of analyzing the data. The first method of analyzing the data was to actually take both detectors, the Louisiana detector and the Hanford detector, and cross-correlate them. And so that we get a thing that looks something like this. Yeah, there's a little movie down here. You'll see what it does. Oh, God damn it. The cross correlation, if it shows, maybe, yeah, there it is on the bottom in green. You'll see that here's the two signals. You have signal and noise in both of these. And you'll see there that when they cross correlate, it's sort of obvious thing when you square it. Here is the signal. They're delayed by 7 milliseconds from one to the other. See Louisiana seeing it first. And here is sort of a curve that is quite important. This is the signal to noise of this thing in the cross correlation. There is that event, and this is the probability or the number of events that you would have as a function of signal noise in the statistics. Let's not worry about these two curves. Take the worst one. You're down at the point where this thing has a chance of being an accident once in a million years, or once in 3 million years. Signal noise is just enormous. But that only shows you one black hole. That's the big guy we were just talking about. Let's go to the other method where you actually are comparing against a noise-free template. This is much more expensive in terms of computer time, and it just takes a long time, a lot of effort. And now what you're doing is you're cross-correlating a noise-free template against the noise and the template and the signal, and you'll see that you get a very good cross-correlation. And now the evidence for that is what you see here. It's the same curve. Here's the signal noise again. There's that event, but there's this event and that event. Okay? And you wouldn't have seen that you didn't see it in the other. Now, I call it 3 events because this is probably there's an 80% chance of being real. We'll get to that in a minute. There's no question about this one, no question about that one. Okay, and now let me show you the bottom of the results. Here is sort of all 3 of these things in a different plot, and here are the numbers. This is the big guy, 36 solar masses of one. This is what you solve for when you do 29 solar masses for the other. And they become, in the process, they lose 3 solar masses when they're all driven into gravitational radiation. Sort of amazing. And it outshines the universe for that few number of fractions of seconds. Complete universe. Here's the one that is marginal. It would be 23 and 13, losing 1.5. And here's one that's for sure. That's much longer, it's much lighter, and these are more like the stellar solar masses that we know about. Okay? And so those are the 3 events. This is, let me not be too ambitious. This is where each one of these came within a month of one event per month is sort of what we're getting. And then if you want to look at the statistics, I don't think you'll learn much from this, but it's sort of required. Here is the Bayesian way of measuring this. This is the mass of the 3 events. Of one of the masses, that's the other mass. And there's the error circle. There's the error circle for the big guy, error circle for the other good one. And this is the one that we're not sure of. Here, for example, we could not find the spin. That's what this is, of the individual black holes. Just not enough data to do that. And here is the relationship between the final mass and the spin of when you have the orbit, and you have those masses, and you then can calculate what should be the spin of the final object. And that's sort of, you can calculate for that, and that's sort of quite reasonable. So again, it shows that. And this is the distance. The 2 that we're sure are at about 500 or 1.4 billion light years, 500 megaparsecs away, or 1.5, 1.4 billion light years away. And this one is a little further out, the one that's not as well known. So those are the kinds of things. And where are they in the sky? And here's where the sadness begins. We can't do very well. Here are the same 3 things. Here is the big guy, and you can say he comes from the south. This is a equatorial polar plot, where our angle is this way, and longitude is this way. Earth, this is RA and DEC, okay? And this is where that one is, but you can't solve for the others, and this is already terrible. Giving this kind of thing to an astronomer makes him or her go crazy. It's 100 square degrees, it's not worth much. And then here then is the possibilities for the other. We just don't know where they are. And the reason is because these don't point. There's a little bit of angular distribution in them. They have a little, when you come in right above, it's this best coupling. They come in from the side, you get less coupling. It's still very much isotropic. It looks like a peanut, the angular distribution, with some zeros along the 45-degree lines.
But if there's a delay from the signal from one...
That's the only way we get the position information, from the delay. That's how these curves come about.
So you get the cosine.
Yeah. No, that's the way that's what he's saying. And that's why I say the delay between them is the only position information we get. So as soon as you have more detectors than 2, that method works a hell of a lot better, as you'll see in a minute. Okay? It's very important. So I just want to quickly show you people who did this, and I'll talk the future, and then I'm done. So this is the guy who actually made the thing work. That's Barry. I hope many of you know him. He deserves an enormous amount of credit. So does Stan Whitcomb, who was a scientist who's been on this thing almost from the beginning. And he was the principal scientist for the project. This was his project manager, who was absolutely critical. He's now working on the TMT, the big telescope. And these are people who were hired by Barry, and they were critical to, now the current deputy director, and this is a systems engineer. It's engineer for the whole project. So one more slide of people, because these are important people. We have the LIGO Scientific Collaboration, which has, NYU is not part of that, but maybe you're trying to, no, you could become if you wanted. Maybe you don't want to. But the thing is, these are people who get added to this and have to do certain things, not just like a high energy collaboration. What you do is you offer to do something, and then you get voted into the collaboration, and if you don't do it, you get thrown out. Okay, it's the same. Look, I'm being a little too severe, but people are. If you have a sensible proposal, you can probably get funding from the NSF to be part of the LIGO Scientific Collaboration. And there's a spokesman. The first elected spokesman was Peter Salson from Syracuse, then David Reitze, who is from Florida, and now Gabi Gonzalez, who you probably know about. And then the directors of the project after Barry was Jay Marks, and now he is the director. David Reitze is the director. And now these people, as you see, the faces get younger. Maybe not her, but she's the same as these. But this is the next generation. And these people are the people who actually made LIGO, the advanced LIGO work. Because that's Dennis Coyne again, who is the chief engineer. But Peter Fritschel is a younger man, and he is the guy who is the head scientist for the advanced LIGO. He's the guy who orchestrated advanced LIGO. He's a guy who's been in this for a while. But these two are very important people. Valera Frolov is the guy who is in charge of commissioning in Louisiana. He made the discovery I talked about yesterday. Yesterday. And Daniel Sigg is the guy who is in charge of commissioning at Livingston, at Hanford. So those are the people who should really get the credit. And this is something cute. I came to New York a couple of days after the announcement, and I saw this advertisement. You can probably read it. It was in your subway. It was, scientists, I can't read about paraphrasing. Scientists can find black holes in outer space, but you have a much harder time finding an apartment in New York with a walk-in closet. Okay? But that was in the subway here. This was taken by my nephew. The New Yorker had this very cute thing in it. This is about the 12th of February. 2 birds. This guy saying, "Look, was that you I just heard, or was it 2 black holes colliding?" Okay. So anyway, somehow this thing got into the public conscience, which is really sort of amazing. Okay. So now with the future, and then we're finished. Here's one piece of the future. This is a question that was raised by you or somebody. What happens if you have more detectors? Or maybe I will tell you. If you have more detectors, you can certainly, this is the error bars, again in the same kind of polar plot, and you can see the huge error bars with Hanford, Livingston, and Virgo. H means there were 2 detectors at Hanford. That's not why they did nothing for this. 1 detector at Virgo, and 1 detector at Hanford was enough. Having 2 detectors there had other reasons, but it didn't improve your ability to get timing differences. Okay? So that's as well as we could have done had Virgo been on the air. It's worse than that. Now, because we didn't, Virgo was not on the air. Here's what happens if you include India in this thing. It really makes quite a difference. And this now gets to be something you could give to an astronomer. You could say, look, we see something about the size of in an error circle about the size of the moon. That's still terrible for most astronomers, but not hopeless. And that's a half a degree squared. Okay? Or a quarter of a degree squared. It's half a degree on the side. So it's very important to have more detectors. Okay, there are other sources we might see, and we've only seen black holes. In fact, we didn't expect to see black holes because we couldn't calculate how many there were in the universe. We had no idea whether black holes came in pairs or not. We knew neutron stars came in pairs from the Halls-Taylor thing. And so consequently here, I won't go through this all, but we discovered black holes first, but we expected to see this first. Well, we didn't. They're just much stronger. But there are other sources. For example, it would be fascinating to see a supernova. But you have to get detectors then that are sensitive enough to go to several galaxies out. I mean, in our galaxy, it's once every 30 years. If you make this detector sensitive enough at the limit, which I showed you, you might be able to get a supernova per year. That's encompassing enough galaxies then to get that. And that would be a fascinating thing. You would learn exactly what's going on in the supernova because gravitational waves don't give a damn. They go right through everything. And you can see exactly into what's going, the bulk motions inside the supernova. It would settle a whole bunch of theoretical stuff that I still don't know. It would be a hell of a discovery. And it would be like black hole normal, as we talked about. Triggered searches, for example, gamma ray bursts. We've been doing that all along. Someday we'll succeed. The idea that you might be able to find gravitational waves in their setting, the sources in their setting using electromagnetic waves, is a very important thing. And that's why we want to add more detectors to this thing so that we can tell ordinary astronomers where to go looking. And then there are sources which are maybe like pulsars, which are completely CW sources. They're just much weaker than these burst-like sources. You can learn a lot about the kinematics of the waves from that. And here, these are not as sharply lined. And then the most fascinating, but I don't think it can be done with LIGO, is to look for the cosmological background. In other words, look at the primeval gravitational waves that might come from inflation directly. I don't think that can be done by LIGO. I don't think it can be done by LISA, which we'll hear about in a minute. But it could be done by another satellite mission, which is taking LIGO and putting it into space. I mean, really LIGO, and we'll talk about that a little more. But we will clearly be troubled by foreground sources, especially now we know about the black holes, we'll see an awful lot of them. So here is sort of the future for this field, and this is well, not a good way of doing it. This is frequency. Here's 10 to the 4 hertz. There's 10 to the minus 16 hertz, or periods. I prefer to talk about periods. 10 to the minus 4 seconds, 1 second. And there's LIGO with its sources we've talked about. Here's a space system with its sources, and there are massive black holes. There are ordinary white dwarf binaries. And this thing has been talked about since 1974, and it's put 3 satellites in orbit around the sun, behind the Earth. And there are, I don't think that, unless you want to, you can ask me questions. I can show you some results from, I won't show them to you, I'll just tell you about them. But I'll show it to you if you ask. Is the business of that they have now put a test satellite up to show that they had the sensitivity to do this. But the arm lengths here are not tens of kilometers anymore. They're millions of kilometers between the satellites. And you're looking at much lower frequencies. And they're guaranteed to see things. Then there's a project called the pulsar timing, which is using a whole bunch of pulsars, just using radio astronomy, measuring all the pulsars that you can get 360 degrees around, all 4 pi steradians, and then looking at whether there are timing changes in them that look like a quadrupole distribution depending on where they are. And what you're looking at then is you're looking at gravitational waves that are going between us on the Earth, where the antenna is, and where the pulsars are. And they will cause changes in the rates of the pulsar emission, at the rates. And that's something that they hope to do, but they're in periods where they're talking about years to certainly fractions of a year to years, maybe 3 or 4 years. And then lastly, a huge project a huge idea that's a much smaller project, but that's been going on now for a while, and I think has real promise, is to look at the polarization of the cosmic background radiation. Look for B modes. What are those? It turns out the density fluctuations in the primeval universe, if there were gravitational waves, are such that the places where you have temperature anisotropies will radiate into places which, hot places will radiate into cool places. And Thompson scattering, which is the same thing that makes the polarization in our sky. When you look at the sun, if you look with sunglasses, and you look with polarized sunglasses, you look where the sun is, you go 90 degrees to the sun, you'll notice as you rotate those polarized sunglasses, the sky gets brighter and darker. That same effect goes on in the universe, but now you're using a temperature as a way of doing that, and looking at the electric fields that come from those thermal radiation plots. And if it's gravitational waves that have excited the density fluctuations, they give a certain pattern in the sky. If it's just scalar fluctuations, they give a different pattern. And that is what's being looked for. And people thought they had seen it about 2 years ago. They got messed up by dust. But I don't think that experiment is over. It's that people are doing it better and better. If there is something to be seen, those of you who are in the know, I think the experiments that are now being done will get to R, the ratio of the tensor to the scalar part, of about 10 to the minus 3 in the next 5 years. And then if they really want to go to 10 to the minus 4, I think they have to go into space with that. And that'll be later. So that's the future for gravitational waves. Thank you.
have already seen that it's quadrupolar by some phase shift in the two places, Louisiana and Washington?
No, which one of the points? What we've seen is we've established that the velocity of gravitational waves, and that's what I think you're asking, is pretty close to the velocity of light from two methods. But we don't know anything about the
I was
polarization.
thinking if the orientation of the arms of the detector at one place and the other were different.
No, but they're not. I see what you're asking. Okay.
They're not?
They're not. No. In fact, let me tell you, that was a big decision. What he's talking about is, had we organized Livingston and Louisiana so that if you take the L's, those L's, and you project them back into the center of the Earth, and they had been at let's say 45 degrees to each other, we would have been able to also turn the polarization of the gravitational waves.
Yeah, that's right.
That we didn't do for a very deliberate reason. And we're hoping Virgo would give us that information, and when they get on the air, they will. But we didn't do it for a very simple reason. We thought about it a long time. We were still in the regime where we were trying to make sure that the gravitational waves, when they were detected, could be detected. And so what we did, we decided deliberately to make those two detectors as on top of each other as close as they could be, so that we could exploit that idea that if a gravitational wave hit one, you would get the same waveform in the other. That was absolutely essential to us. Now, we gave up some science in doing that. And we were hoping that the Europeans would build their detector, or anybody else would be orthogonal, or not 45 degrees to that, and that is indeed the case.
So if you had rotated them, then there would have been a phase shift in the...
Yeah, and you would have had different signals in the two. And we didn't want that. See, in fact, if you work out the binary coalescence, you'll find out that the two have very different waveforms. The two polarizations do not have the same waveform. So we would have given that up. We would have learned something more. Now it would make sense, now that we're sure that we've detected something. But we have that. We have it in effect with the fact that Virgo will go on the air. Yeah.
Any questions? Last?
Can we see the Lisa?
Oh, you want to see the Lisa thing? Okay, sure. Here's the Lisa thing. Okay, it's very fast. Lisa is, what they sent up was a payload. This is the payload. It went to the Lagrange point, to the L1 point. That's the place where these things would be. So where the gravity gradients are minimal, and so where the orbit needs the least amount of pushing around, it almost can stay in that orbit. And I'll describe the instrument they put up. It's better seen in this picture. What they did is they put in that inside, there are two test masses that are free floating. One is completely free floating. The other one has electrostatic plates on it, so you can push it around a little bit. And there's the interferometer to measure their relative separation. That's the instrument they sent up there. And here's the result. It's really quite spectacular. This is now a different kind of spectrum than you see before, but it's related to it. This is frequency. Here is 10 to the minus 2 hertz, 10 to the minus 3 hertz. You're getting the hours. Here, and here's a tenth of a hertz. Here is acceleration spectrum. Acceleration per unit. It's acceleration squared per hertz. And here is their requirement in these same units. This is the requirement for the Pathfinder that they flew. Here's the requirement for the mission, right there. And here's what they got. It's spectacular. In other words, if they proved to everybody they could launch this thing, get it up there, release the masses, and they settled a whole bunch of technology questions. And the Americans gave this up because the taxpayers don't want to have it. We have to work on the taxpayers. Pardon me?
Didn't NASA announce that they would join this?
Well, be careful. That's the history of that is typical politics in this country. What happened was that the United States and Europe went 50-50 on this in the 2000 decadal. If you remember the decadal study that was done in 2010, excuse me, 2010. And that's where the astronomy people get together. They decide what things they will push, very much like the high energy people at HEPAT. In 2012, NASA, because they had overruns in the James Webb, which is their big project, and on top of that, because well, I'll be honest with you, the Republicans were running Congress. They got no increases to make up for that. In fact, they got shrunk a little bit, and they had to make a decision at NASA headquarters what to do. And what they did is they dropped all the projects that were joint with the Europeans. Every one. An X-ray mission, a planetary mission, and LISA. Just absolutely dropped it. And now, because I was on this last decadal, the mid-decadal survey, that because of this discovery, in part, but also because people had come to their senses, the Americans, and the statement of that committee is to try to make it joint again. The Europeans didn't stop it, but they made some very bad compromises. The Europeans, to keep it going, made some compromises which really would have jeopardized the mission, I felt. They got rid of the third arm, and they had only one arm. That's very bad if you only have one shot at it. That's the redundancy you need, and on top of that, you get information out of all three of them. And they did something which they didn't tell everybody, that they made a mission which only had a 2-year lifetime. And that's much too short. And it still cost something like $1 billion. So they made a very bad compromise. It's quite clear they didn't want to do it that way. And the Americans now, hopefully, will get back in. I don't know if they can. But that's the recommendation that's been made.
I was wondering when they announced the size of the black holes involved in the spiral, how they were so sure of the individual masses, and so you know it's the...
Okay, that all comes, I'll tell you how that comes about. It's a good question you ask. I mean, I think if I paraphrase your question, how did we get the initial estimates that were then run by numerical relativity? That's, I think, the way you... see, the model you see was many, many different runs of numerical relativity waveforms, which now can be done with slightly different masses, so they got a best optimization of the waveform that was measured to the theoretical waveform. That's how it was done. But how to begin? And that was done by doing some very simple sort of back-of-the-envelope calculations. As soon as you see the first few oscillations of that, you can do a Newtonian calculation that says how close are these guys and what are their mass. There's some mass. And you can get the ballpark of the thing. And then a little bit, as you can do a lot of calculations still that is not numerical, but analytic, to see how the rate of change of the frequency goes as a function of the difference of the two masses. And so you do those calculations first to bound the general relativity calculation. And that general relativity calculation takes a long time to run. Now it's been speeded up. But that's the one that finally clinched it. That this was a dead ringer for the number that the Einstein field equations gave for the masses, the spins, the aspect, a whole bunch of parameters. And we don't have much data. That fit was the best we could do, the one that you saw.
There's not a lot of degeneracy?
What?
There's not a lot of degeneracy in the parameters?
There are degeneracies, but they don't matter. For example, I'll give you a degeneracy, which is very important. But you can get a little bit of it by noticing that there's a little difference between the two detectors. They're not completely on top of each other. It's using the fact that there's a slight angle between them, you can get a piece of information which is very important. Had Virgo been there, it would have been a piece of cake. But damn it, they weren't. Mm-hmm. And so the thing, but the degeneracy that's really most serious, is the fact, what is the inclination of here's the Earth, here's the orbit. What's the inclination of that orbit? Is it like this, or is it like that? Versus the distance. That is a dreadful degeneracy. And they got some pretty good idea of what it is. I mean, the distance isn't all that well measured, and those were the two trade-offs that were made. The fact that there was no angular, that there is no spin along the direction of the angular momentum of the orbit, the orbital, it turns out not to be very serious. It turns out if you really want to solve for that spin, you would have a degeneracy again. But it turns out you already see that there isn't any modulation in the waveform, which is something you expect to see if there's spin, individual spin, in those two systems. It's very much like the spin-orbit coupling in quantum mechanics, it turns out. And you would expect to see a LS coupling. And that LS coupling would make the oscillation of the magnitudes change. And you didn't see that. So you set limits on, and it's close to zero spin. It may not be, but it didn't matter. You could subdue with spin or without spin. You wouldn't get very much difference in the answers for the other parameters. No, the worst one is the one I just showed you, is the inclination of the orbit vis-a-vis the distance.
When you were showing us that animation, you said there was some phenomena at the end once the collision was done that LIGO didn't observe.
The ring down.
Yeah, okay,
Yes.
right.
Sorry.
That's not that it didn't observe it. The signal of noise wasn't good enough to see it. In other words, the ring down is a factor of 10 smaller in amplitude than the moment. The thing that was a 10 to minus 21, you saw that from the simulation, was when the two things crashed into each other. That was the biggest single piece of the strain. And on the ring downs, which are now the normal mode ring downs, and you can get that very easily. You can make a calculation for yourself. Once you know the mass of the, I mean, it's not a very exciting idea. Yeah, I'm sure we'll see it. But what the idea is fairly straightforward. When you form the black hole pair, make the new black hole, it isn't spherically symmetric. There are two things coming in, and the event horizon around this will form more in one position than another. And then it takes the velocity of light around the event horizon to smooth it out. And it makes several orbits around that, the kink. And that's those oscillations that you would have seen. And they're small, okay? And so people could guess at this. Not that you should. We were going to see them, but it was too small to see against the noise. That's all I'm telling you. Yeah.
Let's take this conversation to the 6th floor. Everybody is invited for the reception. And before that, let's thank Dr. Weiss for